So, applications of signal processing in finance. According to my topic, the overview of my topics is firstly introduction. In this, we are going to cover is signal processing useful, filtering, problems with conventional DSP. Secondly, we have algorithmic trading, in which we will cover causal modeling. And third, synchronous squeezing transform and its examples. And lastly, we'll conclude the session. In the introduction, since finance is a very large and versatile sector, and it has been in process and since working from past 4 to 5 decades. But in early times, the finance and economy were not dependent on mathematics and advanced mathematical processes like signal processing. Earlier, it was used with traditional guessing and guesswork methods, and that would not create a reliable source for digital signal processing. So for digital signal processing, the base work was given by Fisher Black and Myron's Clothes that changed the scenario of finance and economic sectors. These mathematical financial systems made policies that could hence that could increase the investors' trust. This is just an introduction part. So a question arises in our mind, that is signal processing useful in analyzing financial data? So yes, it is much important to analyze financial data, as finance is based on past value and the present value, and by the study of past value and present value we can predict the future value, and this is where the use of signal processing takes place majorly. So signal processing techniques are used to represent and predict the main features of price evolution, and to classify stock as to design diversified investments. Also monitoring the stock prices and financial products, and extrapolating their future evolution according to past available information. As a This can be viewed as a classical signal processing problem. So what is filtering and filtering of time series data? So as we can see in the shown graph, we have the graph as price to index ratio, in which the graph has a versatile nature and is very much complicated to study. But after signal processing with conventional methods and some DSP, we can see that the graph has been smoothened out so as to convert the signals into smooth trend lines. So in this graph we can see that the noise has been reduced using moving averages filter and low pass filters. But recently advanced adaptive methods like Kalman filters are also being used for some removal of noise. Next, we have some problems with conventional DSP that are to be noted down. So as we can see, we have two signal graphs. Each graph has its own spectrum, and to address spectrum is the signal's magnitude and phase characteristics as a function of frequency. So when the graph is plotted against frequency, the spectrum of channel A and B, as we have seen, they both are quite similar, although the signals A and B are quite different according to their natures. So with the conventional DSP, we can see that the graphs are having the same spectrum, although having after having different sign and cos properties. So these can lead us to most concepts in signal processing that we have learned during our coursework work well with stationary signals, that are signals whose power spectral density is constant with time. But in financial sector and economic forecasting, we can see that time series data is highly non-stationary, that is volatile, and due to which and wild and often unpredictable fluctuations that can occur. So we are exploring the new technique to tackle some of these problems while still being computationally efficient. That is synchro squeezing transform. This can be a revolutionary process that can change the direction toward the economic forecasting. Next, we have the algorithmic trading. So, trading a financial instrument by forecasting its value based on some algorithm is called algorithmic trading. It has three parts, that is subjective forecasting. In subjective forecasting, it is done with some prior knowledge, experience, intuition, and guesswork. It is usually inferred from both macroeconomic and microeconomic factors that are subjective forecastings was used in earlier times where we didn't have some mathematical and computational tools. So during that time, subjective forecasting would play major role as people used to use their knowledge, intuition, and guesswork to forecast the upcoming trends. Next is extrapolation techniques, whose aim is to project past trends into future. Common extrapolation techniques include regression analysis method based on error criteria such as mean absolute deviation and mean squared error. So to explain about mean absolute deviation is the absolute deviation from a central point, and mean squared error is the absolute error that is measured between two past phases that are in same phenomenon. These are the meanings of mean absolute deviation and mean squared error. Next is causal modeling. This is an important point where the goal is to predict lagging variable based on leading variable. To explain lagging variables, uh, we can take a simple example like lagging variables can be called as uh, the present value of a particular product and its future value of a particular product, whereas the leading variable can be said as a past value or the previous values of a particular product. This, in simple words, this can be said as a relationship between two variables modeled as a cause and effect. This is a causal modeling. To study about causal modeling, it can be said as a forecasting technique to be useful. It must add information to what is already known. The main issue is how to take advantage of this lead lag relationship to perform prediction. In this spirit, authors have proposed real-time trading algorithms that exploit the lead-lag relationship between a pair of stock prices to forecast the price of lagging asset. So, uh, in the algorithmic trading, people use lead-lag relationship of a pair stock to forecast their prices using the previous assets and the current values. This can be achieved by using recently proposed synchronous squeeze transform, that is SST, to quantify the lead lag relationship. We will study the synchronous squeeze transform in upcoming slides. So synchronized squeezing was introduced in the context of analyzing auditory signals. It is a special case of reallocation method which aims to sharpen a time frequency representation R of t, w by allocating its value at different points t1 and w1 in the real time frequency plane. Determined by the local behavior of R of t, w around t, w, one starts from its continuous wavelet transform Ws of the signal s of t defined as Ws is equals to integration of s of t a raised to minus 1 by 2 phi t minus b upon a d of t. This is the theorem proposed by the continuous wavelet transform. In simple words, this can be said as it is a mathematical tool for analyzing data where features vary from different over different scales. So for this wavelet transform is used as when we predict some economic forecasting of a particular stock, the value of stock does not depend on a single factor. It depends on multiple factors. So as to convert multiple factors into a combined data, we use continuous wavelet transform. We will see some examples now. This is the graph showing SST filter asset compared with normal date trended data. So as we can see, the wave, black wave, solid wave is the SST filtered signal, and the dashed dotted wave is the day trended asset with high frequency price fluctuations. This is a chart comparison of trading days versus the price. So in the number of trading days, the price has risen up and shortened down in multiple factors, and with a high volatility rate. But after applying the synchronous squeezing transform, we can see that the wave we have been acquired has much smoother curves and can be easily used to analyze the data. Whereas if we use the normal wave that we have acquired using price fluctuations data, we can see that it has high frequency and is much more complex to study. So we can say that after SST filtering, the high frequency components were successfully removed from the signal. So this brings to the conclusion that synchronous squeezing transform provides a very elegant and useful way to analyze non-stationary time series data, and is often better suited to applications in finance as compared to the regular CWT, DWT, STFT procedures. These are the conventional procedures that were followed in the industries. Also, the ability to extract long-term phase relationship of signals accurately in the presence of noise makes the transform particularly well suited to applications in the algorithmic trading based on causal modeling. So for financial products with known lead lag relationship, phase and synchronization information can be extracted using this approach for appropriate forecasting and making decisions. This has been verified for a large variety of stocks in, in references I have used are represented here. Thank you.